Hello physics students, Mr. Standerson here, and in this video I'm going to go over some of the basics of Coulomb's law to help you prepare for some future lessons. One of the things to remember is Coulomb's law is nothing to take lightly. Knowing this Far Side comic is very true, and poor Ruben would be conducting these experiments on these helpless little babies for his static electricity. Is really a shame. So use responsibility, use your knowledge wisely, do good for others. That's all I'm going to say. All right, but seriously, electric fields, they really are kind of a central thing that we're going to be talking about, and how we can find the electric field, how we can measure the strength of the electric field, and a few other things related to calculating the amount of force of objects in an electric field. A few things to note is that electric fields are imaginary kind of lines that emanate from charges, and they follow a positive kind of test charge. So if you were going to put a positive charge in the vicinity of another positive charge, we know that like charges repel each other, so the field would be forced outwards. It doesn't matter if I put the charge over here, over here, over here, it's going to emanate kind of in all directions. And because it's a positive test charge, it will be moving away from the positive charge. Similarly, a negative test charge would be attracted towards the opposite negative object. So if we have a negative object, the field lines go towards that object. That's just the idea of direction of field lines. All right. The other thing about field lines is the more there are, the closer they are together, then that emulates and it symbolizes a stronger amount of electric force in that area. So we're going to be using these field lines to demonstrate the electric fields around charged objects. All right, so when we look at this, notice how the field lines from the object on the left are moving away, so therefore that must be positive, and they're being attracted to the negative. So this must be a negative charge over here. Notice also that towards the edges, way over here and way over here, the field lines are kind of far apart and they're stretched out. That symbolizes that there's not as much force in these areas. But here in the middle, there's a lot of field lines that are close together, and that symbolizes more force, more attractive force in this case. All right, so remember, quick review, like charges will always repel and opposite charges will always attract. So when I have two opposite charges, they're going to attract each other. When I have two like charges, they're going to repel each other. And it doesn't matter where the orientation is, it's just if those things are close to each other. If they're opposites, they're always going to attract. If they're like charges, they're always going to repel. All right, one thing that we're going to talk about conceptually now is how do we know what things have more force? If you have charges, maybe they are two positives, we know that they're going to repel each other, but how do I know how much force is actually going to, how do I assign a value to that force, right? The magnitude of that force. And the closer they are, their distance actually makes a big impact on the strength of the force. So the forces depend on a few things. They depend on the charges. They also depend on the separation distance between the charges. If you are to stretch them farther apart from each other, they actually will experience less force. So if we start here with D and we have this much force, 2D is going to only experience this much force. It's going to experience less. All right, also the amount of charge makes a difference. So if we have the same amount of charge, in this case 4 microcoulombs and positive 4 microcoulombs, if we increase the amount of charge on one of the objects to doubling it to maybe negative 8 microcoulombs, then that also increases the amount of force that that charge would experience, keeping the distance the same. All right, so we're going to think about this. If we increase the distance, it decreases the force, and if we increase the charge, it will increase the force. So there must be some relationship around those. In fact, there is. It's called Coulomb's law, where the force of attraction or repulsion between charges is directly proportional to the product of their charges. So notice when we looked at just the charge and kept the distance the same, it increased the amount of force because it's directly proportional, but it's inversely proportional to the square of the distance. So when we had a bigger distance between them, the force between those objects went down, and it did so with an inverse square relationship. All right, so here's our proportional idea here. The force Q stands for the charges. They're multiplied by each other, so the products of the charges. D is the distance of separation between their centers, and that's an inverse square relationship. Okay, so here is an important part of this equation. Because we're measuring force in newtons and the charges measured in coulombs, whenever we look at it in a problem like the previous slide had microcoulombs, we have to convert to coulombs in order for the math to work. Same thing with distance. We have to keep our distance in meters. So always look for that as you're going through your problems. All right, here's another kind of relationship. What we're going to take a look at is this special K constant here. So the constant is a value that we always use when we calculate with Coulomb's law, and it's 9 times 10 to the 9th Newton meters squared over Coulomb squared. Once again, they're the units of meters and coulombs, and those have to exist in our equation. All right, if I solve this equation here for K, I'm going to move the d squared over to the other side, multiplying both sides by d squared. Then I get K times the charges, the product of the charges is equal to force times d squared. If I then solve just for K by itself, I'm looking for the units now. Force times d squared divided by the product of the charges. So just looking at units, we know we measure force in newtons, distance in meters, and it's a square distance, so it's meters squared. Charges in coulombs, and they're multiplied by each other, so a coulomb times a coulomb. That's where we get the newtons times meters squared all over coulomb squared. So that's where our unit comes from for that constant. I'm going to run through one quick example that uses Coulomb's law to calculate the magnitude of force between two charged objects. Our first charged object is a -5 millicoulomb, and the other one is a +3 millicoulomb. And it's separated, their centers are separated by 2 millimeters. All right, and we can use what we know about Coulomb's law to find out how much force is actually attracting these two objects together, because I know one is positive and one is negative. All right, so first things first, don't forget to do this step, super important. Make sure you convert from your millicoulombs into coulombs. All right, double check that. Make sure milli, remember, is a -3rd, or 10 to the -3rd power. So we're going to move that decimal 3 places. Same thing here. Millicoulombs, move it over 3 places, and just millimeters to meters, we're going to move it over 3 places again. This has to happen before you plug in any of your values in the equation. Once you've converted, then bring in your values. K is 9 times 10 to the 9th, and then the product of the charges, so you can just take what we've done here with our conversions and multiply those together, divided by the distance of separation squared. Don't forget that square in your calculations. It will throw your numbers off. You should end up, double check your math, but you should end up with about -3.375 times 10 to the 10th newtons. All right, here's another example where we have a -5 microcoulomb. All right, one other equation very similar to this is we're going to take a look at what happens when they have the same charge. All right, so here we have a -5 and a -5, both millicoulombs. I need to remember to convert. I need to remember to convert my 6 millimeters into meters by moving the decimal 3 places in each case, multiplying by my Coulomb's constant. Double check my math, but you should end up with about 6.25 times 10 to the 9th newtons positive. Okay, double check those, and you should be able to plug the numbers into Coulomb's equation at this time and find answers. All right, here's the thing I wanted to talk about conceptually, though, is the sign of that force is really important. A positive F value, or the positive force, actually is repelling. That tells you that those things are repelling. If it's negative, it's actually attracting. Okay, and you can think about that. If the signs are the same, that's going to give you a positive. It could be both positive, positive, or negative, negative, but as long as they're the same sign, you're multiplying them together, it's going to end up with a positive value here. Where if these signs are different, this might be positive, this might be negative, then your overall equation is going to end up being negative. So one thing to just keep in mind as you're running through these problems. All right, once again, coming back to some of the conceptual math, we know that there might be a repulsive force on this positive charge because they're both positive. We can figure out if the repulsive force is 4 newtons, but we double the distance, right? Remember, the force is proportional to the inverse of the distance squared. So if I'm doubling the distance, all right, 2d, that's like 1 over 2d squared, which would be proportional to 1 over 4. So it's really taking 1/4 of what we started with. If we start with 4 newtons, we're going to end up with 1 newton of force. Okay, so be able to conceptually do that with both distance and with charge. All right. The last thing here, if we're taking a look at the charge, notice in this example, our first one has the same amount of charge, -4 and a +4, the same magnitude, and it has a force of 2 newtons acting on it. This one doubles the amount of charge. We knew conceptually that this was going to be a greater force, and it's greater by the doubling factor because these are directly proportional to each other. All right, so if you have 2 times the amount of charge, you're going to have 2 times the amount of force, so on and so forth. Okay, so if we look here, if we have the amount of charge is 1. Here we're doubling the amount of charge, but we're also doubling the distance. So in fact, that cancels out any gain that we would have by doubling the amount of charge. So they end up having the same amount of charge or force between them. Okay, so here is kind of an extra type of question. I want you to be familiar with Coulomb's law, substituting in, solving for either the distance of separation or the amount of charge, or one of the charges if the other one isn't given, and you know the force. I want you to be able to manipulate that. This is a little bit different because we're involving a third charge. They are all in the same line, so we can think about these forces as kind of vectors, right, where we can add them together. So we want to first calculate how much, and we want to first make sure we convert our centimeters into meters and any of our millicoulombs into coulombs. So I've done all the conversion steps right here, okay? So we make sure we have that ready to go. Why did I choose 2 centimeters here? Because the separation between the 2 outer charges is 4, and there's another charge at the midway point between the first charges. So then the separation between each of these is just 2. What they want to do is find the resultant force. So they want you to combine the forces from this interaction and this interaction to figure out how much is the resulting force. So one of these is going to be a repulsive force. Notice here there's negative and negative, all right? So that's going to be a positive. The other one's going to be an attractive force, positive and negative. Okay, so then when we combine them together, they're going to hopefully have the same answer. All right, so what we're going to take a look at then is our force 1 is going to be between this charge, okay, and this charge over here, separated by this 0.02 meters, and we get about 6.75 times 10 to the 8th newtons. Now, because that's repulsive, that's going this way, so that could be our force 1. The other force is going to tie in the positive 9 millicoulombs and the 5, same separation distance. Now when I add these together, because they're both pointing in the same direction, this is attractive, this is repulsive, it's just like a vector sum. So I'm going to add those together and I'm going to get this total charge for that's acting on that particle. Like I said, this is a bit of a challenge, but not something that's out of the realm, knowing that these forces have the same properties of other forces that we studied in the past. Please reach out if you have any questions. Thanks, and have a great day.